Thank you very much. Yeah. Well, my first slide is something that I'm sure all of you know, and it, of course, translates into entropy. And but I have to first confess to you that I don't really understood what entropy is, and I don't feel so bad because John von Neumann in 1948 said, no one knows what entropy really is. And that's coming from John von Neumann. So it's something that not many people really understood. What I want to talk to you today, though, is not about something I didn't know, but something else. And I call this a new law of thermodynamics, although the title says the third law. But there is actually already a third law, but it is been stated in different forms, at least 3 different forms, and they are rather obscure. And worse is that they are controversial because they're not equivalent. And so I'm not going to use the third law for now, but I believe that someday this new law is going to be called the third law because it is the natural complement of the second law. Okay, but what I will talk about today is not quite about Can you all see? Okay, it's not quite about entropy, but talk about minus negative entropy, and many physicists now use the word negentropy. So this is what I'm going to talk about, negentropy, and this is going to be the new law of thermodynamics. And roughly, what you will see today is negentropy is in fact equivalent, in some sense, to a new concept called local activity. So you're going to learn something really new today. It's about local activity. Now let me begin by motivating the reason for this talk, or the background for this talk. Let's begin with a common experience. Imagine that this is a great hall, and somewhere there, somebody opened a bottle of perfume, and you can be sure that in a few more minutes, about 5-10 minutes later, someone at the far corner on the right would smell perfume. And that's, of course, expected because that's what the second law says, that things are going to eventually become uniform or homogeneous. And we know many examples, of course. You put milk in a cup of coffee, and in about 5-10 minutes, you will have all in same color. It's homogeneous. Or you can make yourself a cocktail. You mix different ingredients, and in a short period of time, you will have a homogeneous mixture. So the point is the evolution towards a homogeneous steady state is the hallmark of the second law of thermodynamics. That's what all of you know, okay? And the second law, just to remind you, there are 3 equivalent statements, but what I will use today is the statement: the entropy of any closed system increases or becomes constant with time. And that is the law that implies, the second law of thermodynamics implies that no structure or patterns can exist within any closed system because it's all uniform on average, and so there is no pattern, and pattern is information, so there is no information. But contrary to what you have just seen, nature, in fact, is full of non-homogeneous patterns that are currently widely discussed under, I call it, a seductive topic called complexity. There are many institutes and organizations that call themselves doing research on complexity. So this is actually what I'm going to talk about, is about complexity. And which means patterns. Nobel winners, among his many statements, says that one of the most interesting aspects of the word is that it can be considered as made up of patterns. And so we're going to talk about a lot about patterns today. First, just a quick picture. You have stripes, you have spots, more stripes. And these are, of course, real patterns. Or you can mix up, you can see hexagonal patterns. If you look at it carefully, these are hexagons. And this is in what's called a non-Boussinesq convection in this location. But these are real pictures. And you can go to solid. This is actually, if you look under the microscope, this tells about the cornea of the eye is actually made of hexagonal patterns. So hexagons occurs all over in unrelated items. And of course, all of you are familiar with dendrites. So these are all patterns that you familiar to all of you. And these are all static patterns. So patterns, the point is it occurs in all different walks of life, different materials, different situations, but you find them all over. And these are quite different from homogeneous pattern that the second law predicted. Then these are static patterns. And then there are also dynamic patterns. One of the most interesting one is if you imagine making yourself another cocktail. I call this the Belousov-Zabotinsky cocktail, where you pour some sulfuric acid with malonic acid and bromate and furan as a catalyst. So unlike the other cocktail that you see where it eventually becomes all the same color, in this case, depending on the concentration you pour, one of the situations that happen is that you see red color that becomes red. So you might think it's uniform, and then but a few seconds later it becomes blue, and then red again and blue. It's a clock. So this is now dynamic pattern. And so there's a fundamental difference between the situation here from the other type, because it changes color. It's actually a chemical clock. And there are many such patterns. If you change the concentration of some of the chemicals here, you would get patterns that look like this. These are all real examples. It's not a drawing. And what you see here are what's called target patterns, but it's not static. This thing actually moves. It just grows and grows and like that. And it's called target shooting because it's just like shooting a target. It's called target patterns. And these are let me just show you. Not only that you have this circular thing, but you can also have patterns that you see on top, and these are spirals. Again, these are dynamic patterns. It's not still. This is just one snapshot, and it moves. And this sort of pattern, dynamic patterns, are what is called auto waves. Auto waves, in fact, are nonlinear waves which propagate at the expense of energy extracted from the active medium. They're very different from other kinds of waves. The shape, in this case, the shape and amplitude of an auto wave remain constant during propagation. And when an auto wave encounters inhomogeneities or boundaries, there is no reflection. Two colliding auto waves would annihilate rather than penetrate each other. And this is very different from, for example, in the electromagnetic wave that you all familiar in physics. When two waves collide, it will have interference pattern. But if you take an auto wave, two of them will collide. There's no interference pattern. If the thing just eventually just disappear, it annihilates each other. Oops. The bulb. do it. Oh, thank you. Yeah. Well, this sort of spiral and target patterns are very widespread, and you have just seen one example of liquids. But this is a colony of amoeba. And when amoeba, as you know, amoeba would feed on bacteria. When there are plenty of bacteria, each amoeba would just go their own way. But when the bacteria become scarce, they will begin to secrete some chemical, and the chemical is the coupling. And soon enough, they will form waves like that. And if you look at this is the target wave, this is the spiral waves, and it begin to evolve. This is over time, you can see. And when it collided, it would annihilate each other. So in other words, auto waves are examples of dynamic waves that are very, very common as well. And more importantly, nerve signals, action potentials, propagating along axons are also one-dimensional waves. Now, this is interesting because the second law of thermodynamics predicts a boring, lifeless, homogeneous, featureless scenario for isolated systems. And yet we see all around us things that are otherwise. And this attracted the attention of many famous scientists, and I call this the great mystery of life, because this is how all the scientists get attracted. Let's start with Boltzmann. And Boltzmann said that the general struggle for existence of animate being is a struggle for entropy. He was shocked, and how can life evolve when second law says otherwise? And in the famous book by Schrödinger, What is Life?, I will quote to you some of his concerns. In this book, thoughtful little book, Schrödinger says, how does living organism avoid decay? He said, of course, we all know we avoid it by eating, drinking, and breathing. And then he said, of course, the technical term for that is metabolism, which is just the Greek word to say exchange. And he said, exchange for what? When an organism feeds upon its negative entropy. So the word negative entropy first appears in Schrödinger's, and he was the one who coined it, negentropy. Okay? But when Schrödinger first coined that, negentropy was actually viciously attacked by many physicists. And when Schrödinger was unable to fence off successfully, because it turns out that entropy, as originally named by Clausius in 1860, is actually rather ill-posed and has no physical interpretation. Boltzmann's subsequent interpretation based on probabilistic arguments was also attacked by many contemporaries. In fact, a great personal disappointment to Boltzmann, which actually many people speculated to his suicide in 1906. And too bad, because only a few years later, his theory was recognized. And if you ever go to Vienna, then go to a cemetery, you will see the formula is in front of his tombstone. So that's Boltzmann and Schrödinger. They're both very concerned about how life is possible. Then come next in line, Prigogine, many years later. Prigogine said that biological order manifests itself by a series of structures of growing complexity. And this is contrary to thermodynamics of isolated systems, which leads simply to the state of maximum disorder. So Prigogine in this famous book said, should we then introduce some new principle of nature called instability of homogeneity? Because thermodynamics, second law, say things got to be homogeneous, and yet it isn't. And so the homogeneous solution must have been destroyed by some instability. So they all have some idea something is needed, but they didn't know what. So, and the key here is that the recognition by Prigogine that for a homogeneous solution media to exhibit a non-homogeneous pattern or structure, the homogeneous solution must become unstable. That's the first important recognition. And subsequently, Leon Blumen, which is a very well-known physicist, highly respected, says that life cannot be understood without reference to life principles. The behavior of living organisms is completely different from that of inert matter. Our principle of thermodynamics, and especially the second law, apply only to dead and inert objects. Life is an exception to the second law or second principle, and the new principle of life. So he was asking for the new principle. He said we need a new principle of life. We'll have to explain conditions that's contrary to the second law. So all of them, Schrödinger, Boltzmann, Brillouin, and others, Schrödinger, Prigogine, Eigen, Gell-Mann, Turing, even Smell, etc., have all been searching for a missing new physical principle. And today I will tell you that the missing new physical principle is the local activity principle, which I will explain to you the rest of my lecture. And in all of this pattern that I've just shown, the static and dynamic patterns, these are all widely written over the last 20 years. There are dozens of books written, and they're all under the auspice called complexity. So complexity is sort of a buzzword that everybody hears within the last 15 or 20 years. And in fact, Hawking says that I think the next century will be the century of complexity. So we are going to talk a lot about complexity today. But the second law of thermodynamics is useless for explaining complexity because we know there are no patterns. Some of the interesting books, by the way, that talk about complexity, Prigogine's book, Laughlin's book, Gell-Mann's book, Eigen's book, and Schrödinger's book, Hawking's book. So there are at least 2 dozen or 3 dozen authors' books with different names. In fact, if you are serious and look into the literature, you begin to see that there are many what I call intimidating research topics. Topics like complexity, cooperative phenomena, dissipative structure, emergent phenomena, far from equilibrium thermal phenomena, order from disorder, phase transformation, self-organization, synergetics. And within the area that people call self-organization, you find topics like emergent, self-organized, self-generated, self-assembled, spontaneous, endogenous, autochthonous, autopoietic, autocatakinetic. Truly, truly intimidating. So I was intimidated, I must admit, when I started to read about this about 15 years or so ago. So I started to ask myself, because when I look into the book, they all have similar examples. So I said, what do all these names have in common? Why so many names? Turns out the answer is they have no definitions. That is the reason. And I will show you just one example. In the famous book by Quark, all of you know, of course, Gell-Mann book. He has a famous book called The Quark and Jaggers. And in his book, these are just a list, I won't read them, of strange names all over. Turn out to all mean more or less the same thing. And just to show you one page from Gell-Mann's book, you see self-organization, self-organized, emergent, emerge, complex, emerge, complexity. So he is using many different words that means the same thing. Because there is no definition. So that essentially the way people did is to use an undefined term to define other undefined terms. I call this the art of tautology. Okay. So this is really unfortunate because complexity is currently a very hard multidiscipline. If you write a proposal and you have the word complexity in there, the chances of being funded is much stronger. Okay, and yet it's strange that people didn't realize that this is a a discipline without a foundation. So I'm complaining a lot about without definition. I must give you a definition. That's my first thing. If you don't have a definition, how can you develop a science? Okay? So my definition is very simple. Not that you have seen the example. I define a homogeneous media is said to possess complexity if it exhibits a non-homogeneous static or dynamic pattern. In other words, typically people talk about complexity when you have a medium that are all made of the same component, the same units. And so when they're the same, therefore you expect things to be the same. And yet when you start to see pattern, you start to say, well, that's complexity. Well, my definition is if you have a media and you can find the media is identical, the units are identical, the cells are identical. In fact, the cells typically have to be very simple because if the cells are complicated, then you can say, of course, you put them together, it will be more complicated. But typically, the cells are very, very simple. And if you take one cell alone, it's almost uninteresting. But you put them together, you couple them uniformly, suddenly all kinds of things happen. That's complexity. So we have a definition. And if you want to prove something is complex, you just have to prove that you have at least one non-homogeneous solution. So it's very simple. So I gave you the definition of complexity. Now we proceed. And as I said, we're interested in a lot about because of pattern, because pattern, in fact, can be thought of as information. Now, all of this, of course, are intuitively obvious to Prigogine, Schrodinger, Boltzmann, Eigen, and German. And so they begin to say, what does it take to exhibit complexity, even though they don't know what it is? Well, Schrodinger was among the first. He said, of course, you need energy. You need a supply of energy. The word that you eat, metabolism, you have to eat, you need energy, okay? Which is correct. And Prigogine come 20 years later, he said, that's not enough. In Schrodinger's time, everything is linear. But Prigogine is a nonlinear person. He said, okay, you really need nonlinearity. Of course, he's also correct. Then comes Gelman. Gelman said, well, you need more. You need to be able to amplify fluctuations, being a very good physicist. And they're all correct, but they're not enough, okay? For example, Gelman said you need to be able to amplify fluctuation. The question is, what kind of fluctuation? A fluctuation in position, in velocity, in pressure, fluctuation temperature, chemical concentration, voltage, or current? And the answer turned out is none of the above. You need fluctuation, but they didn't know what it is. And I'll show you a simple example. You can amplify with a lever, but you will see that that's pretty useless. You can put any number of this lever, couple them any way you want, it will have no complexity. You can amplify with that little fixture that you all use, and you can couple them up, it will have no complexity. Or you can have Black and Tucker, they all amplify. But the thing is not the right kind of quantity that leads to complexity. So you can take two of these, for example, and in the simplest case, put them together and put it in a spring, and nothing's going to happen, even though each of these Black and Tucker will amplify. Or for electrical engineers, all of you know, of course, you can amplify any noise signal by a step-up transformer. Again, it can amplify. But I can give you what Schrodinger wanted. I can give you batteries, any number of batteries. I can give you what Prigogine wanted, nonlinear, any number of diodes. I can give you Gelman's, what he wanted, amplification. And I give you all these other instruments. And I said, build yourself a circuit block and put them together in a cube or a grid. And he would not find any complexity. You find every node will measure the same voltage. So it turned out that the correct answer is local activity. Any system is said to be locally active if and only if it is capable of amplifying infinite fluctuation in energy. That's the quantity that is relevant. You have to be able to amplify energy, infinitesimal energy, okay? You know, it's a very small energy, very small noise of energy, but if you can show that you can amplify that, I said that's locally active. So that's the first definition. Local activity means ability to amplify energy. The local activity principle asserts that the correct physical variable whose amplification is essential for complexity is energy. And I will go as far as saying that negentropy, which nobody knew before, is in fact local activity. And Boltzmann's frustrated search for a missing principle of life against the struggle for entropy is precisely local activity. And so is Schrodinger's hypothetical negative entropy is also precisely local activity, as well as Prigogini's quest for the instability of the homogeneous is also the same answer, principle of local activity. So what is the principle of local activity? As stated now, complex and emergent phenomena are impossible without local activity. Just like in thermodynamics, you say something is impossible if it's, if certain thing happened. This is an impossibility statement. You say that it's impossible to happen unless you have local activity. That is the principle of local activity that I will illustrate later part. Now, from the perspective of research on complexity, we all now know that the second law of thermodynamics leads to a dead end. But the principle of local activity pertains to the opposite system, is the opposite of second law, where entropy is non-monotonic function. It is exactly the missing complementary symbol of the second law. So in other words, this is why I decided to call it a third law, but rather I call it a new law because other people might say that there is already some law that's called a third law. Okay, so the local activity principle is the new law of thermodynamics, which I will illustrate in my talk today. Stated in another way, the new law of thermodynamics essentially says that it is impossible for spatial-temporal patterns to emerge in a homogeneous media unless the states are locally active. Or yet another equivalent statement, 3 words. Complexity is impossible without local activity. Those of you who wanted to get into more depth on this thing, I will be illustrating a lot later today, but I wouldn't have tried to give the formulas. There is a book just came out called A Local Activity Principle, published by the Imperial College Press. There it is, and you will see much of my talk today is given a great more detail here. One of the things that my new principle differs from other proposal is that my principle is rigorous. It's mathematically rigorous. Not only is rigorous, it's constructive. It will actually tell you how it's quantitative. Most of the other people thought are just qualitative. You say, oh, if you think of this example, so they keep comparing example, but you can't compute anything because there were no definition. I have a definition, and I'll show you how to compute. And turn out the principle, the theorem that I will state later on today is very deep, very difficult to prove. But turn out to apply it would take no more than simple calculus and linear algebra. So it's relatively straightforward. Okay, so this is the introduction. Now I want to move on to the area that my theorem actually proved. I thought I have a theorem, and of course you cannot. My theorem, principle of local activity, is for generic and very broad system, as you will see later. But what I really proved mathematically is for what I call a reaction diffusion system, and this is enough. In fact, anybody, if you look at literature, the only people who do rigorous work about patterns are those people involved with population dynamics, and this is mathematicians, genetics, nerve conduction, epidemiology, combustions, as well as purely chemical systems. All of this rigorous work all use reaction diffusion systems. So this is a very broad system that I am considering today, and that's where my theory applies. Reaction diffusion equation is just given by this very simple part. You have a partial differential equation of up to n state variables, and these are state variables at a point in space. And then you have a diffusion term multiply with the Laplacian. These are now spatial variable x, y, and z. These are spatial variable. That's why you have partial differential equation. Now, for example, if you have a one-dimensional spatial system, then you would have only that term, and this would apply, for example, to the action that we're going to talk a little later from the Huxley equation. And it turns out that the diffusion term here, the Laplacian, is exactly a string of identical resistors, positive resistors. And in the limit, this becomes the partial Laplacian. And all of this nonlinearity here, what I call the Huxley cells, I'll come back later on, are exactly described by this term. So you can think of reaction diffusion equation is very simple. It consists of the units, the cells that are identical, and they are coupled by the Laplacian. And we have, therefore, a very simple interpretation. Now, in this one-dimensional terms thing that will come back, the importance of the action is that it generates great action potential, okay? And we want to see why that is so. In the two-dimensional case, again, you have, as always, identical units like this. They're all identical. It could be complicated. It could have many state variables, but they're all identical. And then each one usually is not too interesting. Otherwise, yeah, the area is not interesting. It's point. These are all very simple. And then you couple them with a grid of resistors in two dimensions. That is the result of that inner limit is the reaction diffusion equation. So I'll give you just a quick example. If you put in, make all the units to be this circuit that most of you have seen before, and you want to know how is it possible for such a circuit to exhibit patterns, possibly even dynamic ones. And first thing you notice is that all of these resistors are dissipative. They are all positive resistors. So if anything is going to be responsible for making exciting things happen, patterns, dynamics, like this spiral wave, it's got to come from the cells, not the coupling, okay? So therefore, let's focus only on the cell, the unit. So let's cut this off, because we know that the dissipative part, the Laplacian, will play no role in complexity. So let's cut this off and just examine the unit cell as an example. So cut it off, and now you look at this one cell. All of these cells, are, of course, are identical. We just look at one cell, and you probe it by connecting these two terminals to a small current source. Now, something special had to be in this circuit for interesting patterns to occur. So let me now pull this out and look at it more carefully. So this is a simple one port, and we pull out two wires and we connect with a current source. Remember, the definition is that you apply a very small perturbation in current or voltage, but it's a product that you want because you want the energy. So you put in an arbitrary perturbation of current, and you measure the perturbation per voltage. You multiply them, integrate it over time from 0 to whatever time t, and that, of course, is the energy. Remember, I told you it's got to be the energy that you have to amplify. And local activity now, earlier I gave you a definition, but it's not formal. Now this is the formal definition. You got to be able, if you said for this cell to be locally active, means exactly that you must show me that there exists some current waveform, sine wave or any strange wave. You got to find some. You got to give me one example, and you show me that if you see in general, for example, if this were a p-n junction diode, no matter what signal you apply, you will see that the product of delta V and delta will always be positive. So the integral of that will be positive. It will never be negative. So in general, when it's always positive, we say it's positive. The positive case is the second law. It means everything becomes the same. So what makes it local is that you must show me that there is one signal, at least one. All you need to do is show me one, where you integrate and you form, after some time, finite time t, it's negative. That's the secret. If you can show me that thing, I say that cell is locally active. And so the whole universe of circuits, of cells, of units, and when I use circuit, it doesn't have to be circuit. It can be chemistry, mechanical, whatever, but I can translate it into circuit terms here for today's talk. And it's either locally passive when you cannot find something that will give you negative energy, integral energy, or it is locally active. Those are two possibilities. The locally passive part is the second law. The local activity part, where the cell is locally active, this is where my talk today is the missing law of thermodynamics. Okay, now the problem is you have to find a signal that will have the property integral is negative 0. And this is almost impossible. Because even if you try a million times with a computer, and you find it's always positive, you still cannot say that it's not active, because you have to exhaust all possibility. And so that definition is useless. The good news is that there is a theorem which tells you how to test. This theorem says that if you find the small signal, typically this cell, you would bias it with a battery or whatever, the constant part, a constant current and a constant voltage. That's called the bias point. And then you perturb above it is the delta I and delta V. And if you take the Laplace transform of that and divide it, that's what is called the impedance. And so these are well-known standard circuit theory results. It is called impedance, or the inverse of that is the admittance, where you divide the current over voltage. They're equivalent. And depending on the situation, one may be more convenient than the other. The important thing about this result is that I have a theorem which tells you how to check this admittance. Just look at, this is the zeros, these are the poles, you factor them, and you check them. So it's something that is constructive. You can check, okay? And I have a theorem which I proved. And this is non-trivial, but I tell you this is a rigorous theorem. I can prove that if the cells are locally passive, then there will be no complexity. That's the second law, okay? But let's go back to this circuit now again. Just to give you an example, suppose we imagine you put in a 5-volt battery just to be more exciting, and then all of this resistance considers 1 ohm positive resistors. Now you can see that in steady state, we have to look at steady state because we are looking at equilibrium. And Prigogine said you got to the instability of the homogeneous. So you can see that when at the equilibrium, the inductor becomes a short, capacitor becomes open, so that this 5 volt is now going to be directly at the node, so that every node will be at 5 volt. It's uniform. Everything is uniform, 5 volt. Not very exciting. This is what the case when the system is given by the curve like that, a current versus voltage curve. But imagine now that you can adjust the parameter. So typically, you have some parameter you can massage. If you keep massaging, there come to a point suddenly that you will see that the steady state solution, suddenly the 5 volt becomes unstable. And once it becomes stable, of course, anything is possible. And that's the basic reason for local activity, is that it's precisely if it's locally active, it will become, you can begin to see patterns. So local activity destabilizes the homogeneous solution. This is something that's intuitively obvious by Prigogine, but he never knew how to formulate it. And so I can use that circuit and I can massage my parameter until the slope, in fact, is become negative. All of a sudden, I get patterns like that. For that same circuit, instead of just all 5 volts, suddenly you can get this. These are snapshots, so it's just, like in time. Or by changing some other parameters, massage them, I will get spiral wave. Suddenly I have complexity, okay? Now, of course, there is no free lunch, okay? That's just my way of stating the first law of thermodynamics. And every locally active system must have a power supply. And the reason is otherwise you'd violate the first law. So the physical meaning of locally active cell is the following. The one can use a locally active cell to amplify small signals at the expense of an external power supply. That's what Gelman said. You need to amplify, but you got to amplify energy, you got to pay for it. And for example, for neurons in our brain, it maintains their local levels of organization by burning glucose. In fact, every living cell is a molecular amplifier. And now let's get more specific. Let's look at what's called gastrulation, something that, unless you are biology, you may not have heard before, but all of you and I have come through that process. This started when our mother, your mother's egg and my mother's egg get fertilized, and in quick order, one cell divides into two, 2 into 4, 4 into 8, 16. In about 4 days' time, these cells form a balloon, called a blastula. That's where you and I came from. But Turing, the famous father of computer science, published a very influential paper in biology of all subjects. And Turing was very perceptive. He said, look, he said a system which is spherical. See, this is a sphere, remember, this is a perfect sphere. If you look under the microscope, all the cells are identical. You cannot distinguish from one from the other. So it's a complete symmetry. So Turing said, in this famous paper in 1952, Turing said, a system which has spherical symmetry and whose state is changing because of chemical reactions and diffusion will remain spherically symmetrical forever. Well, it certainly cannot result in an organism such as a horse, which is not symmetric, or you and me. And of course, this is what exactly happened. The sphere, after a few more days, suddenly, it's as if God suddenly puts his finger below. For whatever unknown reason, it's supposed to be symmetrical. But after a few days, suddenly, this begins to become unstable. It destabilizes. In fact, this is just a section. It's just like you put the thing up, and that is the beginning of you and me. This begin to have structure. This is the first early development. This is the intestine, for example, and then they develop into organs, and eventually your lung and the brain. We all went through that process. So Turing was fascinated. How is that possible? How can you something that's totally symmetric or homogeneous and do not get a homogeneous solution? When you would develop the structures that are not symmetric, that is a very deep question. But Turing, being a good mathematician, decided to say, well, perhaps I could, or Turing said, perhaps I could find an example that demonstrates this is possible. And his example is very simple. He said, just take 2 cells. You don't have to take 500 cells. Just say 2 cells, but make it symmetric, identical. And imagine you have 2 chemical concentrations, X1 and Y1 for the left cell, and X2, Y2 on the right cell. They're identical, okay? And then so you couple them by diffusion, so that the X diffusion is a little slower, 0.5 times X2 minus X1. X2 minus X1 is just a difference in the concentration in the excess. And this is just the Laplacian in one dimension for when you have 2 cells. And then the second chemical diffuses faster, say 4.5. Now, Turing was very clever because he had to pick this number just right. You will see later on. Otherwise, in general, he would never get what he had. So he doesn't have a theory. So I'm sure he had to do all kinds of try and error. My theory today, by the way, will tell you exactly how to pick this number, okay? But Turing didn't have a theory, but he was able, with great intuition, and probably spent a lot of time until something works. So this is the equation for the left cell, and because the cells are identical, the same equation up here below, it just changed from subscript 1 to 2. And so you can combine these 4 differential equations into a matrix so that it's easier to see and talk about the significance. So this is the 2 cells. This is the kinetic part. This is the Laplacian part. That's why it's a reaction diffusion. It's the most trivial reaction diffusion equation he can find. Now, interesting thing is here. He looked at these eigenvalues of this matrix, the kinetic part. He found out they're all negative. which means that it's stable. And then this part is the grid, the resistor, which of course is dissipative, and should, of course, you expect all the eigenvalues must be either negative or zero, and sure enough, it's negative and zero. So you have two matrices that both that are stable, okay? And the great insight of Turing is to say that maybe because he picked this number properly, that when you add the two, you may get something more interesting. You can ask your teacher in mathematics, he probably will not know this is possible. You have two matrices that all have negative eigenvalues and add them together. The intuition, of course, of most people, including mathematicians, say is, of course, it will be negative. Turing said maybe that doesn't have to be if you pick them properly. And so Turing add these two matrices together. And if you now look at the new matrix, which is the sum of these two, called a capital G, remember, this is the eigenvalue of the first one, eigenvalues of the second, they're both stable. Add them together, and he found suddenly one of the eigenvalues is positive, becomes unstable. That is the example that Turing was looking for, to say that it is possible. As I said, he doesn't have a theory. He had to find this number in a clever way and through a lot of trial and error. And if you don't believe me, just try it at home. Pick some number. You will see that almost always, if this is stable and that's stable, you add the two things, it's going to be stable. But if you know how to pick this number, using my theory now, it will be trivial, okay? And with that, you get patterns, because the homogeneous solution becomes unstable, and you get, this is what's called, these are called the Turing patterns. You get stripes or spots. So Turing was the first person to demonstrate that there is such a thing that you can have non-homogeneous pattern from homogeneous media. But he didn't have a theory, okay? So he left the problem unsolved. He said, what spatial property must this left matrix possess? Because we know already the right matrix is hopeless. The right matrix is dissipative. Just make things more damp. But something had to happen in this left matrix that would make this destabilization possible. Turing didn't know what it is, but he had an example to show it's possible. 20 years later, Smell come along and say, Turing's example is a bit qualitative. He didn't have an exact formula, and although it's correct. But and it's a static pattern. Smell say, well, maybe he can even make it dynamic. And so he picked the same hypothesis as Turing, say he have two identical cells, except that instead of just two chemicals, he had four. So it's a bit more complicated. And Smell was able to show that, sure enough, the two identical cells will not only be non-homogeneous, but it can exhibit dynamics. It will oscillate, become an oscillator. So this is what I call the Smell's two-cell paradox. Smell asked the question, how can two mathematically dead cells mean that they have negative eigenvalues, so everything becomes uninteresting. But you interact them with a dissipative coupling. The Laplacian is dissipative. The grid resistors is dissipated. You put two things that are already stable and make it more damp, they suddenly becomes alive, they oscillate. That is the question that Smell left unanswered. And in fact, Smell was a bit pessimistic. He said at the end of this paper, he said that any sort of systematic understanding, all analysis seems following. Before one can expect any general understanding, many examples will have to be thought through, both on the mathematical side and on the experimental side. He predicted it's going to take a very long time. It took 40 years or so, and that's where my theory comes in, which would be the solution, how to resolve his paradox. So Turing's instability, or Smell's instability via dissipation phenomena, originates from what I call edge of chaos. This is the second new concept. First, you have local activity that you already know what it is now. Edge of chaos is a special case of local activity. It would turn out that, remember, you can adjust its parameters, and when the slope becomes negative, then suddenly you have boom. You tend to have parameter adjust, and you suddenly say, how do you make it locally active? It turns out that in general, there's a very large parameter space, and it would take a very long time to try to find out what parameter would give you local activity. The interesting new result today is that you don't have to do that. Typically, the really exciting thing is a subset of the parameter space called the edge of chaos, and I will explain to you what edge of chaos next. This is the truly fundamental concept. Edge of chaos is just a special case of local activity, but it is what makes things possible and exciting. So edge of chaos is my next topic, and to explain what edge of chaos is, I'll show you what people now call Chua's reader, because that's what I give my students in class to motivate the discussion. And the phenomena is very simple. I tell you, I give you a box. In fact, I'll tell you that it has only two circuit elements. It's just an inductor and a resistor, that's all. And I connect a battery of E volt, and I would tell you that if you pick these elements, the resistor inductor value properly, you can show that for any initial condition, initial current, I sub 0, the solution is always stable, exponential, and with a time constant 1. See, either is minus 1. So it's completely stable, and it's even exact. So now the interesting thing here is I say, okay, now with this example, I'm going to add a 4-ohm resistor, which is dissipated. You know, if anything, this is already stable. I'm going to add something that is going to make it more dissipative in series with the battery. You would expect that this thing is going to be not so exciting, it perhaps even slower, but it's going to go to a steady state. The interesting thing is it doesn't. In fact, it blows up. How is that possible? Okay, remember, this is stable, and then you put in some dissipation, and it suddenly becomes unstable. That's the reader. And the question is, what is inside this black box that makes this possible? And the answer to this question is the essence of edge of chaos. So edge of chaos is something very deep, very difficult to prove, but basically what you will see now is exactly what makes it possible, which you will understand. And now I will show you how it works. Turn out that the two element is just a minus 2 ohm resistor and minus 2 Henry inductor. Okay? And if you have only one negative, then either one or the other negative, then you have a time constant that is positive, thing will blow up. But when they're both negative, they cancel out so that you actually have a negative time constant. That's why it settles down to steady state. And equivalent, you can say the pole is in the left half plane. So it's well understood. But now, it's also easy to understand now. If you add a 4-ohm resistor in there, 4 plus minus 2 become plus 2. So suddenly, you have a minus 2 Henry, but you have a plus 2 ohm. So your time constant becomes positive. This thing blows up. That is why this, and this is exactly, this cell is on the edge of chaos. That's the meaning, okay? If you don't know that this the capability, you will find that it's stable, just like what you have seen. But if it is locally active, suddenly you can have patterns. This is precisely not just an analogy. This is exactly the reason why this works. And although the proof is much more difficult mathematically, but you will understand this theorem now. So the definition. So what is edge of chaos? I just gave you an example to motivate. So I say an uncoupled cell is said to be on the edge of chaos if and only if it is locally active at some asymptotically stable equilibrium point. In other words, to be on the edge of chaos, you must have two things. You must have stable, asymptotic. So things are dead, just like what Smale or Turing say. It's dead. It's dead DC. Okay, but in addition to being dead, though, it had to be locally active. So local activity does not mean instability. It can be stable and it can still be locally active. So edge of chaos is just a stronger form of local activity. And I have a theorem, as I promised you, that it's no good to give you a definition and tell you things qualitative, but what's important is you got to be able to solve things, calculate things. And the theorem is very simple. You only need two conditions. Say you look at the admittance or the impedance. The condition for S of chaos is that you can say that a cell is poised on the S of chaos if and only if they have two conditions. One is that all the poles must be on the left half plane. This corresponds to a negative eigenvalue, so everything is stable. First condition, it's got to be stable. But the second condition that makes it exciting is the condition when if you take the real part of the admittance or impedance, evaluate it with a sine wave input, and if you can show that there is at least some frequency, this is the frequency axis, there's some frequency that the real part is negative at some frequency. If you can show that, bingo, your cell is on the edge of chaos. And this is the fundamental theory, and you can see why it's easy to calculate. All you have to know is to calculate the roots of a polynomial, because this is a pole, and be sure they're all in the left half plane. And then all of you can manipulate complex number, put in j I omega, and then take the real part and find yourself whether there is a frequency where this becomes negative, something that every one of you sophomores can calculate. So now I sharpen my theory here. I said that cells can either be locally passive, which is the second law, uninteresting, everything becomes no pattern, homogeneous, or it can be locally active, but it will turn out that not every point here will lead to patterns. It will turn out shortly that, in fact, the point that leads to pattern is a tiny, tiny area. I have to make this big so that you can see. And so this is the good news. The good news is that you have a huge parameter space that would be very time-consuming to check, but the real important one is to find a tiny area that is in the edge of chaos. And that's the big deal here, is the edge of chaos. And you know how to calculate them. Now, this is important because of a theorem. I have a fundamental theorem called the edge of chaos theorem, which says that a stable equilibrium state Q can be destabilized. That's what Prigogine and all the other luminaries have been trying to destabilize by coupling to a dissipative environment if and only if the equilibrium is poised on the edge of chaos. So I have now equated the holy grail that we're looking for, something that is really responsible for complexity, is precisely to be sure that you have an edge of chaos region. And it turned out that this is a very deep theorem, by the way, and it's not easy to prove because it involves many things. I'll just give you a quick outline. You need to know something about a nonlinear monotone operator. You need to know something about a high-dimensional analog of mean-value theorem. Those of you who took calculus years ago will recall that there is no such thing as higher-dimensional mean-value theorem. Mean-value theorem, as you studied, is good only for one dimension. And that's still, of course, correct. But it turned out that you can relax that a little bit. You can derive a high-dimensional sort of a pseudo mean-value theorem. That's what you need to prove this. You need to have what's called Lasser's complete stability theorem, something that's very fairly well-known in control system area. But you need to know more than that. You need to know something about Poisson integral, which is a very deep subject very complicated subject in complex variable theory. Not many people knew that anymore today. And you need to know a lot about a positive real function. And finally, of course, all of this, if you're a mathematician, you say, okay, this is all well known for mathematicians. But you need one more thing, which mathematicians don't have. You need what's called Telegens's theorem, which is strictly a circuit theory theorem. This may be the reason why this theorem had not been proved before, because you had to know both, okay? Now, complexity, as a consequence, a corollary of this theorem, I can say that complexity is impossible without edge of chaos. And I can tell you now, Schrodinger's negative entropy is precisely local activity. And I can tell you that precogenous instability of homogeneous can now be stated correctly, rigorously, by the following statement. Local activity is the principle which precogenous has sought in vain for characterizing his intuitive notion of instability of the homogeneous. So precogenous has the right intuition, but he didn't have the right theorem to allow him to calculate things. So edge of chaos indeed is the hidden route through complexity. Now I have defined complexity formally, and now you know what it is, and you have now a formula to calculate them, okay? Now it's very important to realize two things. That local activity is not the same concept as instability. It's true that when you make things unstable, if you have pollen right up, of course it's locally active, but that's not the interesting part. The interesting part is the edge of chaos when it's stable, okay? And conversely, edge of chaos is not the same concept as stability. Sure, it is stable, but that's not the only thing. You have to have the negative, you got to have a real part that of the impedance or admittance that is negative at some frequency. And so this is truly a different, unique concept. Now let me move on to give you some real, non-trivial examples. So we come to Huskin and Huxley. Most of you, of course, know Huskin and Huxley with a classic result where they received the Nobel Prize. Huskin and Huxley essentially got the Nobel Prize in 1961 by virtue of the fact that they came up with a circuit model.
I have to excuse myself for a graduation ceremony. So I want to thank you. Very stimulating. I look forward to subsequent discussion.
Pleasure, yeah. Right. Thank you. Thank you for attending. So this is the famous Huskin-Huxley circuit model. And of course, it is a locally active, but interesting thing is that the reason it works is because it is on the edge of chaos. And I had to make it now more substantive. But you may not realize that no one knows the nonlinear dynamic mechanism which gives rise to the action potential. See, the big deal about the Huskin-Huxley model is that they were able to show that if you use that circuit model and you put it in a computer with a very complicated, there are four nonlinear differential equations, very complicated, but he can show, Huxley were able to show, and that's how they get Nobel Prize, is a bingo. An action potential suddenly appears, you know, and this is out of nowhere. He says from zero to none to something that is about 100 millivolts. This is shocking. You know, this thing just appears. And they were the first one to demonstrate that they have a model, an equation, that would actually produce this phenomena, except that they didn't know why. Why they just said that it can happen, okay? And that's enough to get a Nobel Prize, and it's enough that still is the best model that's known today, that's widely used. Although people don't know why. But most people working on that area, they don't really care why. It's just good enough to realize it will generate an action potential. But today I will tell you why, okay? So you start with the Huskin-Huxley model. By the way, the two the resistor in Huskin-Huxley with the arrowhead turned out to be memristors, but that's for another lecture. That's not important today. But you can bias this at an some operating point, and you have a small signal circuit model, so you can find the admittance. And so this can all be derived from the original Huskin-Huxley paper. So we have admittance, and this is the cell. This is the cell, okay? Now the action potential from the Huskin-Huxley equation is a direct consequence of what I call the subcritical half bifurcation theorem that spawned from the edge of chaos. This is very technical, and most of you never heard of half bifurcation, especially what's called a subcritical case. And I'm not going to bother you with that, but that's not important. What's important is to tell you how is it possible that you have all of a sudden for nothing, and when you have some stimulus, say some flash of light, then you get a very huge action potential. And that travels down all the line from my head to my toe, undiminished in amplitude. How is that possible? Okay, and that, of course, is an outer wave, but how is that possible? Well, it turned out that my theorem will tell you that you can calculate and find a set of parameters that you massage, and with that parameter, you will have what is called a subcritical Hopf bifurcation, and that would allow you to produce the following scenario. I'm going to show you only in 2 dimensions so that you can understand. This whole thing is 4 dimensions, okay? So just imagine you have 2 dimensions in the plane, XY plane. When this Husky has the parameter that's properly chosen in the edge of chaos region, you can prove mathematically that there is such a thing called, first of all, the origin is a stable equilibrium. So that's very important. It's stable, okay? This thing seems to be unstable, but it is stable. So if you are, in other words, perturbing a little bit around the origin because it was stable, it's dead. In Smells language, it's dead. But because it is in the edge of chaos, because of the subcritical Hopf bifurcation, you can actually show that the theorem, this is rigorous, predicts that there is a small limit cycle, the green one. Limit cycle means periodic. But that limit cycle is shown dotted. The reason it's shown dotted is because this is an unstable limit cycle, which means that you have to be exactly on this circle. Then you will have, indeed, an oscillation, a very small sinusoidal oscillation. But perturb it arbitrarily inside of it, it will zoom, get into the origin. So go back to stability, to the DC equilibrium. Or if you're a little bit out of that, it will swing out to a huge circle. This is the ratio. I have exaggerated. Typically, this is very, very small. This is very high, 1,000 times bigger. And so the amplitude is so big. This is exactly the action potential. So that's how, and now this is stable. You can see that if you perturb it anywhere outside, it will convert to that. Or if you're a little outside, it will convert inside. So this is the action potential. And that is proved using my theorem, my theory, and how to calculate a region of parameter. The parameter in this case is just the DC bias. When we have a stimulus, say a visual stimulus, you can think of that as an input current source. The question is, how big should that current source be stimulated to be in the edge of chaos region? And the truly amazing result today here is this. So this is symmetric, so just look at one side, where I external is the stimulus. And it turns out that this whole blue region, by the way, the whole blue region is passive, not interesting. The red region is active, local active, but it is too active. It's actually, the poles are in the right half, some poles are in the right half plane. So it's all things blowing up. And nothing interesting will happen when things blow up. You have to be exciting thing, intelligent thing happens only when you have control, you'll be able to control the activity. Turn out that there is a very tiny parameter range of the input. So small, in fact, I could not even draw it, so I exaggerated it. The range is the following. You can state the range in terms of the current or in terms of the voltage, because at DC, they are equivalent. And you can show, using this theory that I have developed, that if you, first of all, that all the poles are in the left half plane, but if you plot the real part of the admittance function, you find that there are 2 islands. These are the two red things you see. But at the tiny tip of that, you will see that this surface actually would go down a little bit from the surface, becomes negative. That's the negative the condition that we need, that the real part is negative. I mean, this is the real part of the admittance. So it is only in this part where it becomes negative that you have edge of chaos. And as I said, I have to exaggerate in this drawing to show you that tiny area. But area, the range is so really incredibly small. The edge of chaos domain, as calculated from my theory, says that the current the range is less than 2 microampere, and the voltage range is less than 1 millivolt. This is really, really sharp to show you that the theory is actually very precise. You know, you have a huge parameter space, and you zoom in using this theory and tell the theory get you directly to where you should be looking at. And this is quite amazing, okay, as a proof of the power of this theory. And the edge of chaos in the Husky-Huxley neuron, therefore, is so interesting that if the range of the edge of chaos in the Husky-Huxley neuron were to be untuned by more than 2%, there would be no intelligent life. You and I wouldn't be here. There would be no action potential. You know, so this is truly, truly remarkable, and it was predicted by my theory. Okay, so again, to summarize, action potential is impossible without edge of chaos. And because of this theory, we can also now make precise. If you look at books on biophysics or people in neuroscience, they always talk about something being excitable. You know, a nerve is excitable. But nobody really knows exactly what it means. I now have a formal statement here. Excitability implies edge of chaos in the sense that the fuzzy concept of an excitable media, and excitable media includes axons, dendrites, muscle, tissue, etc. So the real fuzzy concept that if you look at biophysics book, they talk about excitable media without really knowing what it is. But I can tell you exactly what it is, precisely the existence of an edge of chaos domain in the media cells. And so now you would understand why I said life is impossible without local activity, because edge of chaos is just a special case of local activity, and that all neurons, in fact, are poised on their edge of chaos. Now, of course, again, to be locally active means there is no free lunch, okay, as I told you. So you got to have, somebody has to pay for it. And what is paying for it is a molecule, it's called ATP. ATP molecule this is the molecule. This is the molecule, it has what's called a phosphate, and it is the severance, that's how you cut it. This is the energy pill. I call it energy pill. This is what supplies the energy. And the way this is done is that there is a molecular machinery called the AT phase pump that's called sodium and potassium pump that makes this possible. So all of this makes sense. I have a theory and tells you when it is locally active, especially when it is on the edge of chaos, and in particular, what drives it. It is ATP, which is the molecule like the batteries that we need. Adenosine triphosphate is the name, chemical name. Now I'm going to go more detail now. Husky-Huxley equation is a very messy equation, and even more than 60 years now, they're they're less than the number of fingers that people go into the detail of the equation. But most people did is they sort of simplified the equation, and by the great majority, people study what's called the Fitzhugh-Nagumo equation, which is a caricature. It's not actually correct, but it is a good caricature in the sense that this is much simpler, two-state variable, and this is now the cell. And Fitzhugh and Nagumo was able to show that even though this is not the correct equation, but they can produce an action potential, and most of the phenomena that's predicted by the Husky-Huxley equation, even though the numbers are not quite right, but it can show the same behavior. So this is why this is a very well-studied equation. And here you have two-state variable V1, V2, think of two capacitor voltages, and you have four parameters. You have C, epsilon, AB, okay? AB, epsilon, C. So in principle, you have four parameters to massage. We apply this theory of local activity and edge of chaos, and we freeze two of the variable. Just look at AB. You freeze epsilon and C, and we calculated the edge of chaos region. As you as I explained here, edge of chaos typically is much smaller region within the locally active region, and in this case, it's the pink region. And it's interesting enough that within the pink region, there is, in this case, there's a little cross here that I would like to call it an organizing center, because the exciting things tend to happen in a tiny area. And this is quite remarkable. Edge of chaos is already a small region, and within that region, typically, it's only a very even tinier region where exciting things happen. And I'll show you why I say exciting things. So, for example, if I pick my parameter, the blue, by the way, is the locally passive region. So if I pick my parameter and say in the blue region, and this is now a two-dimensional, a grid, okay? And you put in the initial condition, say some kind of a random signal, random pattern, and over time, these are the evolution. Everything becomes homogeneous, as expected. Because if your parameter is in the passive region, you will have homogeneous. This is the first law. Not interesting, but for the same equation, if you pick the parameter somewhere here, if you put in now an initial pattern of a pattern like that, over time, I'll just show you 5 snapshots, you get something which is the outline of the input pattern. So what you have here, what I've shown you here is that by just with the right parameter, this particular neuron will actually perform like an edge detector. So that the Husky-Huxley, assuming that this is a reasonable caricature, this caricature say that with the right parameter, you can have an edge detector. And if you now perturb this parameter a little bit off here, but in another region here, all near the cross region, the organizing center, and I put in again some initial patterns, this time a picture of a grayscale picture of a beautiful lady, and it will evolve. Remember, this is an analog. It's grayscale. So everything is continuous shades, okay? But it evolves over time, and finally, you get a binary pattern in the sense that it's either black and white, it's binary, but you still see the feature, and that's what's called a halftone image. That's all, every computer, every gadget that's digital that involves image has to be dealing not with the analog input, but with the halftone. And I've just shown you that the same model with just a different parameter, but very near each other, will essentially make you a halftone converter. Pick another parameter indicated here, and just differ by a few percentage time. Suddenly, with an initial pattern like that, it evolves over time, and it ends up with something that you have seen, or it's called a Turing pattern. So I've just shown you that with the Husky-Huxley, or the caricature, more precisely, the Fitch-Nagumo, the same neuron could produce a Turing pattern. And if I now perturb this a little bit further away, somewhere here, again, all near the cross, with an initial pattern like that, over 5-time snapshot, you begin to see that it evolves into these are spiral waves. So I've just shown you that neurons, assuming that the Husky-Huxley or the Fitch-Nagumo equation is a reasonable model, would actually predict that you can get spiral wave. These are the over time. This is the initial condition. So these are all spiral waves. You can see that this is all moving in time. Remember, it's still the same model. And not only that, if I perturb, just change another initial condition slightly, this spiral wave would disappear and end up with what's called a spatial chaos, because there is absolutely no fixed, because it keeps evolving, but it has a pattern. And this is what's called spatial chaos in the parlance. So I've just shown you quite remarkably one equation, Fitch-Nagumo, but perturbing the parameter very near the edge of chaos, which is very small, you can get all of these interesting patterns that people agonize about, which didn't understand: spiral waves, concentric waves, edge detectors, half-tone circuits, and with one same equation, and that tend to suggest that our brain actually, the reason we're can do so many things because we have the dynamic of being able to do all that. That's why we can be intelligent. And now another equation. Let me change another quickly. This is another equation with parameters A, B, only two parameters. And I can ask myself, this is the famous Giron-Meinhardt equation. Giron-Meinhardt, again, use try and error, but with my theory, I can tell you how to pick A and B so that you will be in the edge of chaos. And with the edge of chaos, I can produce patterns like that. With the initial condition like here, it evolves over time. And if you think that this is time, it's when a shell, grow from a baby and evolve, this is really a time axis. And this will produce a real shell pattern. With another initial condition, nearby the edge of chaos, you will get lines like that. Again, this is time, so that if you think of a baby growing and snail growing over time, you eventually will get these shapes. So that's also predicted by my theory. Or if you pick another parameter within the edge of chaos region, you get patterns like that. And if you roll it again over time, you get this pattern that you have seen. And finally, one more example with this kind of pattern. And if you roll it over time, you get a nautilus. So I've just shown you that you can get all of these patterns just from one equation, which, unlike Meinhardt-Giron, I got it by applying my theory. It tells you where you pick your parameters. And now so far all of these equations, by the way, are reaction diffusion equation. But my theory is true for other models as well. So here's an example called a cellular neural network, which I will come back later on, which is not reaction diffusion equation. And I use my theory. First of all, I pick a parameter. There are only 4, because this is, imagine you have a ball-like thing, and this is just a approximation of the sphere of what Turing was looking at earlier with the plus tool. Think of this as an approximation of that. And if I pick my parameter arbitrarily so that you are in a locally passive region, you get nothing but this same color, completely homogeneous, not interesting. But if I ask myself, where is the edge of chaos? And I pick those parameters instead so that I will be in the edge of chaos, suddenly I get patterns. And this is another demonstration of the power of this theory. Okay? And now I will give you yet another example. This is now something that you would be interested, because this applies to your heart and my heartbeat. It turns out that, of course, the heart pumps blood, it's because they generate action potential as well. And in fact, the equation that is widely used to simulate these heartbeats, this is the electrocardiogram, is just an adaptation of the Huskin-Huxley. This is basically Huskin-Huxley equation, but with some additional modification. And if you use this, it is again a reaction diffusion equation. And it turns out that you can ask, where is the interesting parameter? And of course, as I said, it's going to be in the edge of chaos region. And it turned out that also, because it's the Huskin-Huxley, the interesting region is very small. And typically, here's one example that you're edge of chaos. When A is 58 and B is 100, and you would get a normal electrocardiogram. But what's amazing is that you go off from 58, this is 58 to 100. If you just change by per 0.5, a very small percentage of time, all of a sudden the heart stops beating. And this is quite amazing, because this happens in real life. You have heard, of course, a lot about sudden cardiac death. This is one could argue that this is perhaps an explanation that why people could suddenly drop dead. And this is actually quite often. In the United States alone, you may not realize over 1,000 lives are lost every day to sudden cardiac death. And we can now understand why that's possible. because the area, the region of the parameter of the edge of chaos is typically quite small. Okay, let me move on to yet another subject. So far these are all reaction diffusion, but I promise you that it doesn't have to be reaction diffusion. Take most of you know what a CNN is, so I'm going to take a CNN. It's just another architecture, and where you have the cell, they are identical cells, just like all the other you've seen, except that in this case I'm going to have coupling to the first and second nearest neighbor. So I have parameters, I have a 5 by 5 neighborhood. Now every cell would interact within the 5 by 5 neighbors, okay? And I'm going to, these are all parameters. I'm going to even fix that, and I'm going to just vary the center parameter. I'm going to vary this so that it will be in the edge of chaos. And you will be amazed that the interesting thing happens when this is within a very small domain only. Now I also have a DC parameter, Z, which is a constant. Usually is 0. But in today's example, I would allow that to be a DC, a constant. So I have two parameters to adjust. A parameter, the coupling center, and the constant. In most cases, most of the sample, this is actually 0, so you can ignore it. So it is this number that is important. This is the number that essentially tells you when you are getting into local activity and finally when you get into edge of chaos. So I will start with the number 24 minus 24.2. That's the smaller. I'm going to keep increasing that number. And with this constant to be 1.2, you will find that this would evolve for any random initial condition into a hexagonal pattern. I've shown you earlier a hexagonal pattern. Now I can show you that this one model will produce hexagon. See, this is a hexagon, okay? This is our hexagon. It will produce hexagonal pattern. But for the same cell, by just changing from 24 to minus 23.25, and with a random initial condition, suddenly the hexagonal pattern suddenly became Uyghur's patterns like that, something that looked more like stripes. And by changing the initial condition, you can actually have what I call a hallucination pattern. This is all produced from the same equation just by massaging the parameter. In fact, it's the same parameter with a different initial condition. And this already shows you that you can produce other patterns. One can now ask the question, how does the leopard, for example, get its spots? And you can ask, how does the tiger get its stripes? It turns out that it's easy to understand by going to the edge of chaos region, and in this case, just change a little bit, minus 23.25. Okay, and then now I'm going to adjust my constant from 0 to 1. Okay, and remember the first one is minus 1.2. Now I'm going from 0 to 1. So I have a very small range to adjust, and I'm going to adjust this one. Earlier it's minus 24. So we just have perturbed a very tiny bit. You will see that the pattern, when it's 0 to when it's 1, goes from left to right. So you have these stripes pattern on the left, and then to these spots on the right. And this, of course, it can mimic that the leopard spots and the tiger stripes. And you can also say that this happens with the zebrafish, because the zebrafish has spots and stripes. And by adjusting this central parameter a tiny bit more to minus 23 points, exactly minus 23. Remember, we started from minus 24 some, okay? Now we just end up to minus 20. Already, you can see all kinds of different patterns. This is now yet another form of pattern. And this pattern is also very widespread. This is like a tuning fork opening to the left. This is like a tuning fork opening to the right. This happened in many occasions. For example, if you go to the Sahara Desert, you will get patterns like that. And if you look more carefully, you can see that these are the tuning fork patterns, okay? And so this is the same equation just by massaging the parameter. But what is even more interesting is you may not realize it, but if you go to a zoo the next time and look at a tiger or a leopard, you see that the tail is unusual. The tail is made of stripes like that. Well, even leopard, even though have stripes, but the tail will have these little stripes. And so now how is that possible? This is the kind of a tail that looks like. And so biologists have struggled for many years to try to understand how is that possible, okay? And if you look at the cells look all alike. So how does a cell know that it had to be produce stripes and not dots, for example? Well, it turned out that you don't have to work hard. It just used exactly the same parameter in the case of chaos that I had, except that in all the example I have has been rectangle or squares. But this time, so, because this is a taper thing, so if I put myself an area that is a taper and just put this in the computer, you get exactly what that you don't expect, but that's exactly what you see. So it's just the boundary condition that will already give you the pattern, and it's within the predicted edge of chaos region. And by changing finally to the smallest number to minus 21.9, so we perturb to less than from 24 to minus 21.9. Within this, I've shown you all kinds of patterns that are possible from the same example, okay? And now in this case, I can have, starting with the initial condition that called it a sheet, a little cross. It evolves over time to eventually dendrites. Remember I showed you early on the snowflakes? Well, these are snowflakes. You may object, say that this doesn't look like a snowflake, which is 6-4 symmetry. Well, that's because we're on Earth. But if you go to Mars, where it is carbon dioxide snowflake, then they will exhibit a 4-4. If you look at the molecular structure of carbon dioxide, you would have this 4-4 symmetry, exactly what I would just show you. And this is all just simulated by perturbing by tiny bit the parameter within the edge of chaos region. And now even more exciting is something more about life now. Okay, so far those are all you can say static pattern. But what about this little organism? This is a tiny little about 5 millimeter organism that lives near the lakes or ponds. This is called hydra. Hydra is an interesting animal. Is that they have self-repair. Hydra is a small animal capable of self-repair. You cut off a hydra's head, and a new head will be grown. You cut off a hydra's leg, a new leg will be grown. Okay, so it has this capability of self-repair. How is that possible? But that's what life is. I mean, we get sick, we recover. How do we? You cut yourself, you recover. How is that possible? Well, using the same example, just change the parameter. Just change it to minus 24.2. And all the other numbers remain the same. Just this tiny bit. You can show that with a random initial condition, this is what you get. So you can think of this as now as the organ, if you wish, that has this structure. And now I'm going to cut this organ as if you are hurt, and so I'm going to cut this out, cut a part of so you are really hurt. And then you put it in the computer as the initial condition, and look what happened. It evolved over time. Eventually, it recovers. It repairs itself. That's self-repair. Nothing magical. It's all the work of the dynamics from the tiny parameter and edge of chaos. Okay, so I hope I give you enough example to motivate how this theory works. And now for the remaining time, I want to tell you now some kind of intuition. So far, everything is rigorous, everything is mathematics. But now I can give you a little bit more intuition of how this works. Turns out that what is basically, not all, but most of the cases are what I call positive feedback. Positive feedback is a typical mechanism that produces local activity. Now, I'll give you an example. What do you mean by positive feedback? You can put this experiment when you go home. This is a very old slide, in old-fashioned, but imagine that you have a TV screen, and the TV, instead of connecting to the antenna, you have a camera that looks into the screen. In the beginning, it says, oh, noise, okay? But what it recorded here is become the input to the television. And then, of course, then this thing is going to produce another pattern, and then this will focus, and it keeps feeding back. That's what positive feedback is. Look what happened when you throw that just this simple positive feedback loop will produce from the initial just snow, suddenly something that is varying, even with color. Beautiful color. These are all, none of them will ever repeat. And these are patterns, okay? These are non-homogeneous. And so this is an example of what I mean by positive feedback. A more now down-to-earth example are lasers. All of you know how a laser works. It essentially have mirrors on both sides, and you have atoms that you have to excite, okay? In fact, the physicists actually use the word active atom. They didn't know what local activity is, but they use the right word. The atom had to be activated, okay? And you activate the atoms by pumping, by injecting some current. And if you don't pump enough, the atom is not going to get synchronized, and you don't have laser action. It's just like if you think of every one of little cartoon men here, everybody walk his own way. You know, they don't care. But if you think of this as a parameter, the pump is the parameter. You're trying to get you into the edge of chaos, okay? And suddenly, when you reach the point where you're in the edge of chaos, all of these people just, without realizing, suddenly cooperate. They are now all in sync, okay? There was no conductor. Nobody say, face forward or whatever. It just suddenly you synchronize. And this phenomena, of course, is a positive feedback again. And what in fact happened, if you look at the equation of the model that the physicists use, initially when they are not synchronized, you have a transfer characteristic that looks like this, where every input would be only one output. But suddenly, as you pump in, you adjust the parameter, and when you get finally to the edge of chaos, this becomes vertical, and then eventually it becomes like that. Then suddenly you have three solutions. That is where you begin to have local activity in the edge of chaos region. And basically you can explain this by what's called, physicists like to say, symmetry breaking. When you are not in the edge of chaos, you have only one bottom. Every solution is the same, homogeneous. As you pump, as you vary parameter, when you get into the close to the edge of chaos region, these begin to flatten up, and when a certain critical value is reached, suddenly this thing would stick up in the middle. It's all of a sudden you have three equilibrium. This is unstable, and these two are stable. This is how a laser works, and you can understand this because of the positive feedback. And in chemistry, there's such a thing called autocatalysis. This is the frequently, in fact, observed form of positive feedback. And Prigogine is one of the contributors. Prigogine tried to understand the BZ reaction, the Zabosinski-Belousov that I showed earlier, when you have this spiral wave or this color chemical clock. Well, he was able to show derive the equation. Essentially, because he's a chemist, he was able to figure out that with three reactions, the first reaction, you have two molecules, A and B. But first, a molecule A will be converted to a molecule X. This is the intermediate molecule. The second reaction, the molecule B that is already in the solution would then interact with the X that you produced, the intermediate one, and produce a third molecule, a fourth molecule Y. And the third reaction is the critical one. You cannot take two of the molecule X plus Y and produce 3X. So now you can see from a single X, a single molecule called X, you produce 2 and finally 3. So this is amplification that Gelman was talking about. You must be able to amplify, where now you're amplifying the matter, which of course is a form of energy. And now I will show you some even more exciting thing to show that when we talk about complexity, typically you start with something very simple. But if you couple them together with the right parameters, suddenly strange things happen, amazing things happen. Let's look at a colony of ants, something that is real. Ants, by the way, individual ants are quite stupid. And that's what you see. So we were something that's stupid, okay, to make things interesting. Ants are really individually are stupid. I tell you why I say that, because no one has actually succeeded to teach individual ants to do anything. And for example, you understand why I say that. You take a starving ant, that's really starving, and you put him through a bifurcation tunnel, and you always put sugar on when it bifurcates, you always put it on the right-hand side. You would think that the starving ant would quickly learn that you must always turn right, okay? It turned out that it doesn't. No matter what you do, no matter how starved, it will still make mistakes, it will still go to the left. And cannot teach an ant even when it's starving. It's stupid, okay? But, however, you put many of them together, a bunch of them together, if you have sufficient them, and what marvels of collective behavior suddenly occur. But a lot of them would suddenly hook together, can result in a remarkably interesting and quite unexpected behavior. This is the very essence of emergent behavior. The word that you see, emergent, is sort of come from this kind of behavior. And the reason this works is that the ants are sort of lazy. They like to just rest, and then they will move randomly, and it's chaotic, and nobody would get synchronized. So if you start with a few ants, something say less than 10 ants, and you record in a camera how many ants over time are moving. Most of them would be sort of just lazy and don't move. So you can see it's random. There are 5 ants, there are 6, 8 ants over time, and there are times when nobody is moving. It's completely random. But if you now increase the number of ants from, say, it's about 8 to the next one to about 20 ants, and so at a different time, all 20 will be moving, but again, it's random. You increase the number, this is the parameter. We're trying to get into the edge of chaos region. Get it to 30, it's still, 40 ants. It's still, you're getting close to the edge of chaos, but so as long as you're not there, nothing is interesting happening. And finally, you get to about 100, all of a sudden, it becomes pure, suddenly it becomes sync, just like the laser, okay? So interesting, because as the number of ants exceeded some threshold, all of them suddenly decide to take a coffee break simultaneously every 25 minutes. Very precise. This is quite incredible. And this is all predicted. We have actually a model of this on the CNN, and it does exactly like that. Okay. So by the way, the local activity principle, now I'm going to get a bit more ambitious. So far, everything is rigorous. Okay. And I even give you the mechanism, something like a positive feedback makes sense. But now I'm going to generalize this to something that is not rigorous because no one has the equation. If you give me the equation, I would produce the answer. But now I'm going to try to show that the local activity principle, qualitatively, it could be applied, generalized to non-physical systems. I'm going to show you something about worldwide waves, economic system, and social system, for example. Let's take a worldwide wave. All of you, of course, are fascinated by worldwide wave. And it turns out that valuable web pages tend to accumulate incoming links. And pages can become more valuable by linking to other valuable pages. So you begin to see some kind of a positive feedback when it is become more valuable because people to interact. So the positive feedback in the World Wide Web comes from a circular influence that web page authors and users have on one another, taking actions that are influenced by the other. And you can even go further. You can talk about waves. Blocks, for example. Block is actually locally active in the following sense. The amplification property, remember, we have to amplify, okay? That's what German said. You have to amplify, okay, things. Now, the amplification property of blocks results in many interesting social phenomena on the wave. Propagation of MEMS on the wave can start with a single block side distributing a funny or unusual link. Suddenly, all other block sides exhibiting almost a flocking behavior will redistribute the MEM, which impacts not only the content that people read, but also the link that persists on the wave. So in this way, ideas and information can circumnavigate the globe multiple number of times in a single day, making the circular influence linking pattern all the more pronounced. Classic example of positive feedback. And all of this thing, if you think about it, is what I call an extreme events. Like from nothing, suddenly you get action potential. That's, it doesn't go through, it slowly go up, but it has to be very fast because you need the instantaneous, almost instantaneous reaction. I call them extreme events. Extreme events are abrupt catastrophic phenomena such as tsunami, gigantic earthquake, stock market collapse, housing bubbles, etc., whose occurrence were preceded, just before this happened, nobody can predict it. The housing bubble or nobody can expect and predict it. This is exactly edge of chaos. Before this happened, you were dead. You're almost dead. You didn't know it, but because it's calm, and then suddenly boom, that is edge of chaos, the classic sign of chaos. And I want to show you an example that I claim is an edge of chaos phenomenon. If you're an anthropologist, you will know Cambrian explosion in the following sense. About 550 million years ago, unparalleled explosion of life, in the sense that more than 50 major groups of organisms emerged suddenly. When we're talking about 50 million, this few million years is nothing in geological scale. Out of thousands of millions of years, during that period, with a matter of very few million years, all of a sudden, from our recorded fossils, we know that at least more than 50 major species suddenly appear. How come? Okay, it's an explosion of life, and I suggest that that's precisely because the parameter of the nature had evolved in such a point that you find it into the edge of chaos. And the edge of chaos, the organizing suddenly is the lead to the Cambrian explosion. So stock market crashes, I believe, originate also for locally active economy. Even riots, we are now going a little bit further, more ambitious. Even riots during demonstrations are triggered by locally active interaction among demonstrators. And certainly, now of course I have no basis, I have no equation, but somebody, if a psychologist give me a realistic model, and I would tell you that I will be able to pin down the edge of chaos region, that where creativity is a manifestation, okay? And now the last part, two more things interesting is self-reference. Self-reference is an example par excellence of positive feedback. Now I will give you a very important example you will never forget. Imagine you go to Chung Chau Island, that little tiny island, you have a village. There's only one barber in that village. And that barber is very idiosyncratic. He said he has a condition. I shave only men who don't shave themselves. Okay, there's only one barber in the village, and he refused to shave anyone who would shave themselves. And this paradox is not mine. It's in fact from Bertrand Russell. It's called the barber's paradox. And in Bertrand Russell's paradox, the village barber will shave all those in the village who do not shave themselves. The question is, who shaves the barber? Think about it. Well, if the barber does not shave himself, let's say, one possibility, then the barber would shave himself because he shaves anybody that doesn't shave himself. So the barber will shave himself. Okay? But if the barber shaves himself, then the barber does not shave himself. That's the rule. You see that? This is the classic paradox, that very deep paradox, by the way. The barber's paradox is an example of self-referential dynamics. It's positive feedback. resulting in local activity, in my opinion. So self-reference is an example of positive feedback. And indeed, this is so fundamental that within the framework of classical logic, the Barber paradox is undecidable in the following sense, that by showing the paradoxical statement could appear in ordinary language and logic, Bertrand Russell has shown that the standard method of logical inference are too weak to resolve even simple questions. And this is very interesting because I claim, or I suggest, that the Barber's local interaction rule is Bertrand Russell's paradox is locally active. In particular, it's got to be in the age of chaos if properly modeled by equations. Now, fast forward, say 30 years, comes our ultimate hero here, Gödel. All of you have heard of Gödel. Gödel in 1931 proved that there are mathematical propositions that can be seen to be true but cannot be proved to be true. This is quite amazing. And this result, an example of this, for example, all of you may think this is nonsense, but everybody says every even number is the sum of two primes. It's called a Goldbach conjecture. Obvious, right? It's obviously true. Nobody has succeeded in proving this. Nobody. And in fact, people use computer, they have done trillions of times and still correct. But it only takes one negative answer, and so people still keep going. But nobody has proved this. And the reason is that called a Gödel's incompleteness theorem. Essentially say that there are true statements that can never be proved. And in this theorem is so deep, in fact, and so important. This is perhaps the deepest theorem ever. Even Einstein believed that Gödel's incompleteness theorem is the deepest intellectual creation of the human mind, an example of emergence par excellence. And so I would say that Gödel's incompleteness theorem is in fact mathematical equivalent. But by the way, this is how Gödel proved his theorem. It's very deep, so deep that few people understood it. But the basic idea of the method that Gödel came to be able to prove his theorem is to show that his theorem is mathematically equivalent to Bertrand Russell's Barber's paradox. So that Barber paradox turned out to be truly deep. It is the genesis of the Gödel's incompleteness theorem. And because I claim that self-inference gives you the Barber's paradox, I also say that local activity is the origin of Gödel's incompleteness theorem. And we can now go beyond, a little bit more ambitious, even go to literature. Most of you probably know Thomas Mann got his Nobel Prize for this famous book, The Magic Mountain. And it turned out that Thomas Mann, even though he's a novelist, is very intuitive. And what I'm going to show you some paragraph, some quotation, which show that he actually was talking about local activity. So he was just like Shorin and all the other people that we have just mentioned. He's interested about life, how life is possible, the mystery of life, okay? So in one of this page of this huge book, Thomas Mann say, what then was life? Well, Thomas Mann say, it was the warmth generated by the form-preserving instability. Now we begin to see the word. It's the instability of the homogeneous, and the warmth is the power supply needed to generate it. So he's got the idea expressed in literary way. But go back to Immanuel Kant, which is fascinating. Immanuel Kant, in his classic critique of judgment, says the following. He says an organized, remember we talk about self-organization. Immanuel Kant already was talking about that. He said an organized being is then not just a mere machine, for that has merely moving power. He said machine is not impressive. He said, but it possesses in itself formative power. Formative power, remember, is where the intelligence comes from, okay? That's where you get into the age of chaos. So it's a formative power of a self-propagating kind, which it communicates to its materials, though they have it not of themselves. It organizes them, in fact. And this cannot be explained by the mere mechanical faculty of motion. Immanuel Kant was already using the buzzwords like self-organization, and he actually had a feeling, the right idea that something that self-organizes themselves, and that, of course, means, if he knew it, a local activity at the age of chaos. So I may want to summarize that what I've just shown you are numerous examples, but supported by a rigorous theorem, and essentially proved without any doubt, because the theorem that life is impossible without age of chaos, that age of chaos is in fact the pearl embedded within the domain of local activity. Because local activity is such a big region, but it is really where you are in the age of chaos, which is tiny, that all these exciting things happening. Okay, that's what creativity happening, because it had to create, and that's I call this the age of chaos is the pearl of local activity. And remember, this pearl is accessible by all of you, because all you need to know is to factor the roots of a polynomial and find the real part of a complex number. Bingo, there is your port, that's your age of chaos. Okay? So the new law, summarized again, of thermodynamics is the local activity principle, whose pearl is the most relevant, is the age of chaos. And now I can even say that the second law of thermodynamics sentences us to death, right? But the new law gives us life. And together, essentially, there are two parts of the coin of entropy. That's why I would believe someday people would think that to call my new law the third law, because it's the natural complement of the second law. And it doesn't matter the timing. My law is within the last few years, but the first law of thermodynamics, the conservation of energy, is called the first law, but it's not first. Conservation of energy was known much later than the second law of thermodynamics. And yet, by logic, the people would classify now the first law of thermodynamics is conservation of energy, and the second law is the entropy increase. And now this is logically the third law, although there is already a third law that are, by the way, controversial, as I said. And logic would someday dictate that we should call this the third law. So I end up, not quite yet, but almost, okay? I have a cartoon to summarize what age of chaos really means. Age of chaos is like you're looking for the needle in a haystack. The theory of local activity tells you where not to look, because the part that you don't want is the local passive. Don't look at the locally passive part. But the part that's locally is still huge. Age of chaos tells you exactly where to zoom in. That's what the cartoon says, okay? And now, finally, I have two more short examples to conclude. If you talk about entropy, you have to talk about Maxwell's demon. Most of you probably have heard about it, Maxwell's demon. For those of you who do not, here is what Maxwell's demon is. Maxwell's demon is a thought experiment designed by Maxwell. Our Maxwell equation, same Maxwell, okay? Maxwell proposed this Gedanken experiment. He said that you have, think of a devil, okay? And you have in the beginning, you have two chambers. The devil can open and close the trapdoor. And he would just observe these are the molecules that are moving in arbitrary direction, random. Some are higher, some with lower velocity. But the devil would look at this different molecule, and whenever he finds a fast-moving molecule, he will open the trapdoor, let it go. And remember, the second law would say that if you have an open thing, eventually everything will be uniform, homogeneous, no information. But this devil would observe which molecule is fast and open trapdoor only when you have a fast, and then eventually the right side would be the fast molecule, the left side would be the slow molecule. You have suddenly, without, he didn't put any work. or energy. And he didn't give any energy to the ball. And the second law said that you can never go from, transfer heat from a colder to a hotter place, right? That's what a second version of the second law. And this violates the second law because without expending any work, eventually you will have, the cold and hot chambers. And then, of course, you can now drive an engine. Violates the second law. So that's the famous Maxwell's demon. And nobody has successfully yet explained how is this possible, because it violates the second law. The best explanation that is more or less reasonable is to say that even though the devil didn't put any energy, transfer any energy to the molecules, but the devil has to measure the speed. He had to have a photon, an eye, and so he can measure the speed, right? And that act is an act of measurement, requires energy. And now I agree that is a reasonable solution, and I would resolve the paradox by saying the devil, the demon, is locally active, whose entropy production would make up for any deficit in the entropy balance. So the second law is still correct, is not contradicted by virtue of the local activity principle. And finally, the last slide that I have is a fun one. My students love to do this, and I believe some of you would. And I'm sure in Hong Kong, you can go buy a bottle of Tia Maria. It's a liqueur, really, really pleasant, not too expensive. Go buy one and do this experiment, and you will love it. This is my favorite cocktail. Pour yourself in a little glass some Tia Maria, which looks like a dark color, and then pour some milk, about 5 millimeters of milk, white thing there, okay? Now, early on, I showed you that when you can make cocktail, you pour things together, eventually you have one color. But not for Tia Maria, and especially when you put in milk, because over a few minutes' time, instead of things become homogeneous, it got structure. And I'm going to magnify this. This is the structure. And it's actually, the cocktail tastes even better when the structure forms. Okay? It violates the thermodynamics, second law, right? So question, what makes a Tia Maria cream possible? And of course, now you will know the answer. This local activity generated by chemical reaction. End of my talk. Thank you for sticking around. Thank you.